arteries, really coming from the U-leg, from the artery in U-leg, and navigating all the way up to the coronary arch with a long U-arch region and into the brain, into the small artery, into the brain.
In this episode, I'm talking with Christophe Chautems, an ETH alumni who specializes in medical robotics. He's currently CTO and co-founder at the ETH spinoff, Nanoflex Robotics. This is the We Are ETH podcast, and I'm Susan Kish, your host. Christophe, if I look at your career, it would appear that you really like robots. Is that correct?
Yes, that is true. I spent the last 15 years working in robotics in different fields.
Very cool. How did you get started looking at robotics?
For the beginning, already before starting my study at ETH, I was looking what can I study, and I was interested in computer science, electrical engineering, mechanical engineering. And robotics was just at the crossroad of these three fields, but there was no robotic study at this time. So it was EPFL microtechnique or ETH in electrical engineering or mechanical engineering, and decided to learn German and come to the ETH Zurich.
Very cool. And the first thing I read about you doing was the Robo Cup in 2009, where, if I understood correctly, you competed in the nano robot category?
Yes. It was one of the first projects during my study. Was still during my master at ETH Zurich. Then we had a competition, a class where we had to drive micro-robot on a 2mm field and pushing object onto it towards a goal. It was the first time I was starting doing programming, autonomous control. We had to drive the micro-robot driving autonomously on the field.
And that sounds like that was probably a lot of fun. Tell us about what the Robo Cup is.
The Robo Cup is usually robots who are playing soccer. You have probably all of you already seen this video of robots trying to play soccer when they try to beat the world soccer team by 2050. And for a couple of years, they've done a micro scale of it with micro robots. We were playing on a really small field. So the goal is, you can move object of a 2mm field, pushing a ball that was 550 micron height. It was quite challenging, and that was led by Prof. Brad Nelson, the team, and as a student, I was working into this team.
So did you track this on a microscope, or how do you actually watch the game?
Yeah, you are watching the match on a microscope with camera so that you can screen it on other screen. So yeah, it was really under a microscope.
That is very cool. And how did you grow up in Switzerland?
Yeah, I grew up.
Is that why you were looking at EPFL and the ETH?
Yeah, I grew up in Switzerland, coming from Canton Fribourg, but quite away from Fribourg, between Fribourg and Neuchâtel, in between two lakes. So yeah.
That sounds idyllic.
Yeah, it is. It's a really nice region, really a nice spot to grow up. When you have 3 lakes at less than 5 minutes far away from your home, it's amazing.
I can imagine. Now, I had understood you did an undergraduate degree in Sweden.
I did an exchange in my bachelor. I went for I went there for 1 semester for 6 months to get Stockholm during my bachelor degree.
That's the Swedish equivalent of the ETH?
Yeah, it is the Swedish equivalent of ETH.
Fantastic. And once you finished your undergraduate and you did your master's and your PhD, all through all this, you kept on looking at robotics. And it sounds like magnetics and how magnetics direct robotics, or what's the red thread there?
I think I was mostly working in robotics. So when I was in Sweden, I was working on grabbing object with a hand, also looking how we can best grab objects. So I was in the robotic field. Then I was more working on spatial robotics, or you can drive rover autonomously. But at some point, I decided to move away from spatial robotics and going towards medical robotics. In the first job in a startup, who was coming basically from the same lab where I was doing the nanogram RoboCup, and then start working on medical robotics. I found it more impactful, the medical robotics, that you can have more an impact on the life of the people by developing new solutions for helping people who need treatment.
It looks like you spent some time at NASA.
Yes.
And Eames. That was where you were doing the planetary?
It's what I did, yeah. I was at the
navigation.
I was doing it in my master thesis. I was recommended by Prof. Sigwarts, put in contact with the NASA AIM, and I was able to go there and doing all my master thesis, spending 6 months programming robots to drive autonomously on Mars and the Moon. It was a research project looking how fast can you drive when you only have camera available because you don't see more than a couple of meters in front of you. And you're in an unstructured environment. You're not driving on the road. So you need to be able to brake quickly if something show up in front of you yet you don't know. So
oh dear, there's a cliff.
Especially the cliff problem. A cliff, you don't see it more than 2 or 3 meters away because your camera is just there. So you can imagine if a road is suddenly has a cliff, you will not see it way before if you're driving because it's kind of hidden if it's not flat, the ground. So that was the biggest challenge. How fast you can drive on braking before you fall on a cliff if you don't know what is around you. So that was kind of my research topic.
There's a rover on the moon right now. Didn't it just land?
I don't think there's so many rovers on the moon, but they are more in Mars at this point of time. The NASA had a couple of rovers driving at this moment on Mars for years. So there was some rovers sent to moon recently, but I stopped a little bit following that. I'm more busy with the medical robotic field.
Medical science.
Since I left that 10 years ago, I don't know exactly what is happening, but I still hear some of this project that I was involved into it. I know going sand to space, and so it's quite a long time frame between the development of a robotic system for spatial exploration and the time is landing somewhere. It's really long project and even more challenging than the medical robotic because if there's a problem, you cannot fix it. So there's no way of sending someone for doing a service.
Fantastic. And also you had to do, because some of the work you do at Nanoflex sounds like it's remote. So that does sound like that's a common theme between that work you did.
Yeah, it's exactly common. So we are working, especially after the NASA with the ESA, we are working we can teleoperate robot on demand with a couple of seconds of delay because you have the time for the command to go there, coming back. This teleoperation problem is the same that we are handling today with Nanoflex. Yeah, because we want to teleoperate a robot. So if the doctor is not at the right location and the right spot and the patient is getting a stroke, that he can operate the patient from a distance because when you have a stroke, basically a blood clot in your brain, every minute counts and you don't always have a doctor who is there waiting on the patient coming at the hospital. So it's really important using technology for helping these people, and so what we're doing in robotic. And it's both is teleoperation problem.
So I was reading, let me rephrase that. I was attempting to read some of the papers around the technology that you work on at Nanoflex and around things like, I think it was called distal vasculature. And I was sitting here going, I don't know what you mean by distal, and I'm a little confused about what vasculature is. So can you explain this in really simple terms,
so
please?
Vasculature is basically all the artery that you have in your body. For us, when you're talking about vasculature, it's really coming from your leg, from the artery in your leg, and navigating all the way up to the coronary arch with along your heart region and into the brain, into the small artery, into the brain.
Let me just make sure I get this right. So you're inserting something in an artery in your leg.
Yeah.
And it's going to go all the way from the leg, up your body, and into your brain? Like a yard, a meter?
Yeah, like a meter, yeah. A little bit more probably, because it's not all straight, but around a meter, yeah.
Doesn't it have to wiggle on its way up, like around your internal organs or a bone? Or
It's basically following the artery, but there's a lot of curve and a lot of intersection. So it's like a road that you need to follow, a 3D road you need to follow all the way. And you need to be able to steer the tip. So today, when they're doing that, they have a tip with bend at the tip, and they rotate it, rotate, push, using different tube with different shape. But it's extremely difficult, and you need a lot of skill and training to be able to push a 1 meter tube through your artery all the way to the brain. So for us, what we are doing in Nanoflex, we are providing a system which generates a magnetic field, and we can orient directly the tip like a compass. By changing the direction of the field, we change the direction of the tip. So we can point in the direction where we want to do, and then push it forwards to reach the right location, making it easier if you control the tip, as if you are pushing something and controlling it for 1 meter away.
Okay, so it's as if, again, I'm going to use horrible analogies, but as you said, you've got a compass, north, south, east, west, and you're telling it, because somehow you know that it's going to have a hard turn to the right, so you need to go east by northeast.
Yes, is that what we are doing it? Except we are not only doing that in 2D, northeast, but in every direction in 3 dimensions. So we can also go up and down at the same time, making it we can point it really precisely in any direction. That make the navigation way more easy to do for a clinician.
That's why there was a picture of a joystick on one of your websites.
Yeah, because for controlling that, we basically use a joystick. It's like a computer game. You are using basically the joystick for controlling the direction of the magnetic field and the advancement of the device. So we are doing that with a joystick. And we use basically this magnetic technology for making the navigation easier. And at the same time, we have a soft tool who make less damage to the blood vessel or can be less risk of perforation. And with that is also making it easier doing teleoperation. We already have all the infrastructure using the joystick, using the magnetic field, that we can just use the joystick for anywhere in the world for controlling the tip of the catheter.
Oh, that's cool. Again, I have to just say this back to you to make sure I get this. So you could have a technician in Zurich who's looking at a screen, and he or she has a joystick in front. And it could be somebody in Ann Arbor, Michigan, which is where I grew up, but they have a fabulous hospital there too. But let's just pretend, right? St. Joseph Hospital. And the technician locally has inserted successfully this item in an artery in the leg and has the magnet thingy on top. And then the joystick person directs it, so it migrates up the body into the brain?
Yes, it's exactly that. It's exactly what we are doing and what we are developing.
That is, as the expression, as we would say in Boston, that's wicked cool, right?
Yeah, the first doctor we are using it were quite impressed. So we have done demo between the Mayo Clinic and Zurich, where they were controlling from the Mayo Clinic with the joystick, the system in Zurich. We had the right type. Yesterday evening, a paper published in Science Robotics with as attachment the video of the doctor from Mayo Clinic steering the device in a silicone model in Zurich. But the next step is doing that into a patient. So we are working towards that.
So once it's up in the brain, then what does it do?
So basically, the first application we're targeting is ischemic stroke. Is when there's a blood clot into the brain, which doesn't allow the blood to flow to part of your brain. So in this case, we want to go to this blood clot and aspirating this blood clot to remove it. And when we remove it, then the blood can circulate again in the anterior brain, in the artery where blocked before.
What does aspirate mean?
Aspirator. You basically apply some pressure. You basically remove the liquid into basically.
So it's a loop of air?
It's not a puff of air. It's like a vacuum cleaner, more or less. But you are just aspirating the flow, the liquid into the catheter. So you basically...
so you flush it out?
We flush it in, more or less, into the catheter to removing for the patient.
Oh, and then it flows all the way back out?
Because you have basically, we put a tube, a catheter is basically a tube who is going from the leg to the thing, and then you basically flush it in the catheter and pulling it out through this tube. Now,
this sounds like this is a process that is slow, but you mentioned earlier in the conversation that you've got this 3-minute window. So how do you...
You don't have a 3-minute window to do the procedure. So if you have a procedure, usually every minute count, because every minute where the brain doesn't get blood flow, the cells die, the neurons are dying. But usually they want to do this procedure. They want to do this procedure in the first 6 hours, but if you can do it faster, it's better. After 6 hours, the advantage of the procedures is reduced. So usually, optimally, you want to do it as quickly as possible. Optimally, 2 hours after onset of the symptom, it will be good if you could have removed this blood clot. There's no time limit when it's best to do it, but every minute that is delay, it's worse. And the problem if the patient is coming to an hospital and who doesn't have this service, you need to transfer to another hospital. It quickly takes 2-3 hours for getting the ambulance, putting into the ambulance, driving into the hospital, bringing it to the operating room. So if you can operate remotely, it will really be helping a lot. And it's a new treatment. Ischemic stroke is quite new that they're doing this kind of aspiration of blood clot. They only started really removing blood clot around 10 years ago, that they realized in clinical studies showing the big benefit of treating the patient.
Just when you think 10 years in the future, what are the other applications that this kind of robotic technology, especially now that you've got the introduction of generative AI. What are the other applications this could have for medicine?
I think in terms of application, we're really focusing in Nanoflex of providing access to healthcare to everyone, people with a distance from the center. So we will look towards heart disease, coronary disease. If you have a heart attack, there's also a procedure we need to be done quickly. There's different procedures in the vasculature where you may want to treat the patient quickly, but you're also looking towards endoscopy. If you can steer endoscope into the stomach for scanning, detecting tumor early, providing some service in local community by the doctor just controlling it remotely. But we're also looking moving forward. So technology will enable bringing more AI to the operation. Now, AI has been mostly focused on analyzing, imaging it. But can we connect the AI to also helping controlling the robot? Because the advantage of robotic, it can standardize better the way we are moving a device. We can move the device in a more controlled way. So if you improve the control of the device, for example, in endoscopy, we could get better image, better quality, more reproducible image that will be easy to process to AI and getting better outcomes. So all technology can be combined with AI to even improve the outcome that you have in AI. And we're also working toward providing assistive feature. Part of the feature can be done by the robotic system, like we have seen today in car. We have some lane following feature, so we can start implementing feature for helping the navigation of the catheter to the target point, but aligning the tip with the direction of the blood vessel so we can follow better your artery, and then moving forward to provide partial automation and helping the doctor doing the procedure, because there is for sure a big difference. You need to imagine when someone needs to do the procedure at 3 a.m, it's a young fellow, it can be challenging, but then the robotic system...
They've been on call for 30 hours and a little bit tired.
That is a real problem because, what you are doing, you're on call, you're 30 hours, but you're only people who are available for doing the procedure. So you do it, but the technology can help them. And we are really providing access to teleoperation, but we realize is also our biggest need. This hospital have sometimes, it's quite regular having hospital, we have only 3 people for providing 24/7 service for this kind of neurovascular procedure. So you may imagine having 3 people that need to be always one of them available to be in hospital in half an hour time. It's extremely stressing for them. It has a big impact on the social life, and they were also being data. We are showing it there's a high rate of car crash accident, because imagine you are calling in the middle of the night, you have to drive to the hospital, you didn't sleep for quite a long of hours. There's no miracle. No one cannot sleep for 30 hours and being extremely aware. So there is a problem, and it's the same problem. You cannot bring this kind of procedure to more distal region because you have less than 3 people doing the procedure. They cannot provide 24/7. But at the same time, if you have less than 100 patients and we need a life-saving procedure, you cannot build a center because you will not have enough procedure, because they need to do 20 to 30 procedures per year to be good at doing it. So the only solution of providing this service to people who are not living in big city, in city for 50, 100,000 people, is having center connected together, one specialist per city, and they do the operation telerobotics in the different centers. It's the only way of saving 20 people life in a mid-sized city. Only the technology can help bringing that moving forward.
So if I look back at your background and through your stories, it sounds like out of your 15 years of professional life, it's been 13 of them, as I think you mentioned, were with ETH in some form or other.
Quite a lot.
How has ETH been important in your life and what you're doing today?
I think it's been a great place to be at. It's an incredible place to meeting people, think about innovation, looking what the future could look like. I always had an amazing time being at ETH in Zurich. And I was coming to ETH, leaving, coming back. So I travel quite a lot, but every time I end up coming back around ETH. So. And
how did your experience there prepare you for your position as a CTO?
I think ETH is really doing the bachelor, master. They're really focusing on giving you the basic, fundamental understanding it. Because the only time you really have the time to understand the fundamental in terms of physics, mathematics is during you at your time. When you are moving out of ETH, there's a whole range of skills that you need to learn. The way it's working in the academia is quite different from the way it's working into the industry. So I think ATI is really giving you the fundamental to be able to build on top of it. And then you have a lot of skills you need to learn later, but without the fundamental, it will be a challenge moving forward, especially when you have so complex technology project that you need to move forward.
And Christophe, how are you involved with the ETH today?
Today, you are basically Nanoflex Robotics is supported by Zurich. So that was an accelerator funded by AnswersWIS, by the donation from AnswersWIS, who help projects in the medical field, regenerative medicine, robotic field, to move towards a commercial product. Because you may understand that there's amazing research done on ETH, but then the gap between the research done on ETH and getting a startup is quite big. So we have received this support from Zurich, who is kind of a joint accelerator from ETH Zurich and University Zurich, who have provided us office space funding for 3 years so that we were able to work on the fundamental technology developed at ETH to bring it to someone who can go towards a commercial project, basically bridging the value of that of deep tech project. Because for investors, earlier they were saying it's too early technology, it's too fundamental, it's too far away of application. So you are not able to fund money for doing that. And they are trying basically bridging this gap, providing money when they're coming out of the fundamental research, but moving towards commercial application. Because you need a lot of resources to bring disruptive technology to the market. And that is part of ETH, the Zurich.
Very cool. Very cool. Christophe, thank you. Thank you for explaining this in terms that I can actually understand. And thank you for all the work that you're doing. This sounds fascinating.
Thank you.
I'm going to close with some of the standard questions that we ask our guests. And the first one is, when you were young, when you were a little boy growing up between these two beautiful lakes, what did you want to be when you grew up?
I think I want to be an inventor. I was dreaming being an inventor, building things, putting things together. At the end, it's more or less what I have. We are filing patents, we are finding new ideas, bringing new technology. It's a little bit different than the way I was imagining it as a kid, where I was trying more building stuff by myself, because now every research is multidisciplinary. You don't only need to bring electronic software people. We need to bring a team, a multidisciplinary team to work together to bring breakthrough. But it's not too far away what I was thinking about as a kid.
And what are you learning about today? What are you curious about?
I always like to looking at problems that are difficult to solve and can have a big impact. I'm driven by challenge. I'm always driven by challenge. I like when something is difficult to look if it's possible. And usually my approach is always looking at the problem, estimating, is it possible to solve it, or is it outside of the bound of physics? There's no solution. If it's possible but difficult, is what is interesting me. And so it's usually what is driving me to move forward. So I'm always looking to learn more, extending my range of skill to be able to bring people to work together and bringing some complex project to an end. Integration is really my interest. Bring people to work together on the system to work together.
So Christophe, I'm going to move you from the abstract to the specific.
Yes.
So that means you are reading about what, right? And if you had 4 hours in a given day, would you listen to a webinar about a particular topic, or would you read a scientific paper about a topic? What are the topics? What are the areas of technology or the world that you're reading about?
I'm reading about a broad scope of technology, usually really more technology-focused projects. So I really have a broad range of interests going for. I always try reading something new on a new subject. So I'm usually not staying too long onto one.
Like what? What are you reading now?
It depends. It's changing every day. And so usually at the moment it's quite a lot into the teleoperation scenario, or we can bring new design of the internet. So at the moment, I start reading about the CERN network. I see you have interviewed someone before, because for bringing this teleoperation, we don't also need to provide robotic, but we also need to rethink the way internet is working to be more reliable and more performing. So that is one thing I was reading right now. But I'm always strongly interested about technology, process, or you bring people to work together, or you bring innovation. So I have a strong interest in technology. Since a kid, I was more reading technology thing than.
And when you do go into Zurich, what is your favorite place, either in Zurich or at the ETH?
Usually I like going towards the Leighton, being able to swim in the city, in the middle of the city, in the river. It's really a nice spot in the summer for taking a cold dip, or also in the winter for taking a cold dip. So, yeah. I really like the Leighton in Zurich, being outdoor.
Fantastic. Christophe, thank you so much for your time. I really enjoyed the conversation.
Thank you.
I'm Susan Kish, host of the We Are ETH series, telling the story of the alumni and friends of the ETH Zurich, the Swiss Federal Institute of Technology. ETH regularly ranks amongst the top universities in the world with cutting-edge research, science, and people. The people who were there, the people who are there, and the people who will be there. I'd like to close by asking you to please subscribe to this podcast and join us wherever you listen. And give us a good rating on Spotify or Apple or YouTube, wherever you listen, if you enjoyed today's conversation. I'd like to thank our producers at ETH Alumni and LE Media, and to thank you, our listeners, for joining us.